Excellent. Thank you so much. I appreciate that. So welcome everyone to a deep dive on Amazon EFS. So today's session, it's really structured around four phases people commonly go through when evaluating and adopting a storage solution. So the first phase, we're going to be unveiling Amazon EFS. We're going to give you a foundation of what that service is and where it could fit in the services that you provide. The second phase is really kicking the tires. It's testing and tweaking the platform to get the most out of it to best serve your needs. Phase 3, we'll talk about ingest, so ingesting data into Amazon EFS. Then phase 4, we'll talk about what does it take to actually run a workload on Amazon EFS. So with that, let's go ahead and get started. So first we want to unveil Amazon EFS to you. So remember, when you're thinking about storage, you typically think about these three attributes when choosing a storage platform. So you want to identify what the storage type is. You also want to identify some of the features and performance of that storage type. And then definitely economics plays an important role. So there are typically three types of storage in the cloud, in Amazon. So we have file, block, and object. So with file storage, this is when data is stored as files in a directory hierarchy. Typically, this is shared over the network so multiple clients can have access to the same data set. The next type of storage is block. And this is when data is stored on blocks and it is presented to typically a single instance or a single client. It shows up as a locally attached disk. There are a number of services we provide within AWS that provides block storage. And then finally, we have object storage. So this is when data is typically stored within a container. This container is called an object, and there's lots of metadata associated with that object. There is no hierarchy structure. So this is basically all this information, or the file is stored in a flat space, and you gain access and interact with this data, this object, using simple API calls. So this is where you would get or put data based on the key of that object. So why is file storage then so popular? Well, it really works natively with operating systems. So operating systems, they rely on file systems in order to interact with the data in this hierarchy. It also provides shared access to data for consistency guarantees and locking functionality. So typically the data is shared with multiple clients, and it requires these consistency guarantees and locking functionality so that multiple clients can get access to that data and it can maintain its data integrity. There's also a hierarchical namespace within file storage. So that's something that we logically look at and organize data into within this hierarchy. So it makes it very easy for us to identify where this data is. So how does file data compare to some of the other storage types within AWS? So here we see block, file, and object storage, and we see how they relate to each other in terms of throughput and latency. So we see that block storage has really the lowest latency of the three storage types, but it's unable to get the throughput that file and object has to offer. So really depending on what your needs are and your use case, file data may satisfy some of these requirements. And it's definitely important when you're looking at a workload that needs to share data across multiple clients. So before Amazon EFS was introduced just a little over 2 years ago, if you needed to have file storage shared across multiple EC2 instances, a lot of customers did sort of a do-it-yourself file storage environment. So with this, it would look like this environment. You would have multiple clients accessing a file server. This file server would have multiple storage volumes attached to it. But to increase its availability and durability, you would need to somehow replicate this file storage to another availability zone, to another file server, another EC2 instance. And attached to that EC2 instance, you would also have to have other EBS volumes attached to it. So again, it's a little complex to do it yourself with EC2 and EBS. But luckily, 2 years ago, we launched Amazon EFS, and this is a fully managed service that makes it easy to set up and scale file storage in the Amazon cloud. So, with a few clicks in the management console, you can create a file system that is accessible from multiple EC2 instances via a file system interface. And it fully supports, file system access semantics, strong consistency, and file locking. So it's a great way for applications and users to share file data across and among each other. So when we designed EFS, our first core tenet was simplicity. Since it's a fully managed service, there's no hardware, networking, or file layer to manage. So really, with a few clicks, you can create a scalable file system in just a few seconds. So the pricing model is also simple. We wanted to make sure that we had simplicity across the entire gamut of the service. The next core tenet we built Amazon EFS on is elasticity. So with this, file system automatically grows and shrinks as you add and remove data. So there's no need for you to provision storage capacity or performance. You really pay only for the storage space that you use, and there are no minimum fees associated with it. The third core tenet is scalability. So with Amazon EFS, file systems can grow to petabytes of capacity. So the throughput of the file system can drive and scales automatically as the file system grows. And it also provides low latency and consistency across the entire file system, regardless of the file system size. So this really allows a file system to be connected from multiple or even thousands of concurrent connections to get access to that data. So all three of these tenets are built upon the foundation of high availability and high durability. We wanted to make sure that the data was highly available and available to you when you need it, and that it is durable. So when you needed to get access to that data, it was there to serve up to you. So let's talk about the performance modes of Amazon EFS. So there are two different performance modes that we offer. When you create a file system, you would select one or the other. So the default performance mode is what we call general purpose. And this is recommended for the majority of the workloads. We do recommend when you create a new file system and you're going to be sort of kicking the tires per se, that you create a general purpose mode file system and test your application using this file system. The other performance mode we offer is what we call max IO, and this is really recommended for scale out workloads. And let's go ahead and compare and contrast these two different performance modes. So what is it for? So with general purpose performance modes, they're really for latency sensitive applications and general purpose file sharing, while max IO file systems are for those large scale out data heavy applications. So the advantages of the general purpose performance mode is it has the lowest latency, versus the advantages of max IO. You virtually have an unlimited ability to scale out throughput and IOPS, so it can continue to scale and scale. So some of the trade-offs though between the two, with general purpose mode, there is a limit of 7,000 file system operations per second, while with max IO, you don't have that limit, but it comes with slightly higher latencies per file system operation. So again, you need to sort of determine which performance mode is best for the application of the workload that I'll be using with it. Lastly, when do you want to use it? So again, general purpose mode is the best choice for most workloads. That's why we recommend you first using general purpose mode file systems. But with Max IO, it's really designed for these large scale out workloads. So if you have a workload that needs to be accessed from hundreds or even thousands of instances concurrently, then you really want to consider looking at a Max IO file system. So we also offer different throughput modes as well. So with the bursting throughput mode, again, this is the default, and it's recommended for the majority of our workloads. And this is when the throughput of the file system is dependent on the size of the file system. So the more data you add to the file system, the more throughput you're able to achieve. The other throughput mode is provision throughput mode. And this is where you can identify and set the throughput of a file system independent of the amount of storage for that file system. So this could be designed more around or used more around maybe you need to ingest a large amount of data to start using your file system. You need a lot of throughput even though you have a very small amount of data. That is a good use case. There are also other use cases, maybe in some of the HPC offerings or even media and entertainment, where your data set is relatively small, but you need high levels of throughput. So that's when provision throughput mode would be probably most appropriate. So let's go ahead and compare and contrast these two as well. So what is it used for? For bursting throughput mode, it's really for a varying throughput workload. So if you need to burst to high levels of throughput for a short duration, and then scale back down to normal throughput, bursting throughput mode is really the way to go because you're able to do that. There's a bursting model built into bursting throughput mode, which allows you to burst to double your baseline throughput for short periods of time. With provision throughput mode, you can have higher consistent throughputs for those workloads that require that. So some of the advantages, so with bursting throughput mode, it's automatically scaling. So again, as you add more and more data to your file system, it automatically scales and gives you more throughput. The advantage of provision throughput mode, it's user defined. You set the throughput that you need. Do you need 50 megabytes per second? Do you need 500 megabytes per second? Again, regardless and independent of the size of the data, the amount of data you're storing in the file system, you can set the throughput that your file system is able to achieve. So some of the trade-offs with bursting throughput mode, it is a fixed throughput to storage ratio. So again, it's 50 megabytes per second per terabyte of data stored is the baseline, and you can burst to double that when you need to. So with bursting throughput mode, and you have a burst throughput of 100 megabytes per second per terabyte of data stored. While with provision throughput mode, there's a separate charge for the amount of throughput that you provision. So again, these are some of the trade-offs between the two. Bursting throughput mode is really the best choice for most workloads because most network shared file system workloads are bursty in nature. So you're able to take advantage of that high level of throughput for short periods of time while keeping your cost sort of in control. While with provision throughput mode, you're able to ingest and achieve higher levels of throughput independent of the amount of data that you need. So if you need more throughput than what is available through the bursting throughput mode storage ratio that we have, then provision throughput mode may be the right performance mode that you should be using. Now you can switch back and forth between these modes, and we'll talk about that a little later. So again, with provision throughput mode, the throughput is independent of the data stored in your file system. You can increase it as often as you need, and you can switch or decrease the provision throughput mode once every 24 plus hours. So as long as it's been more than 24 hours since your last decrease, or since you switched from bursting throughput mode, you're able to make a switch or a decrease of your provision throughput. So in terms of security and compliance, So to control access to the file system, you would use standard network controls that we have within a virtual private cloud. So those would be a VPC security group and network access. So if you're familiar with Amazon VPCs and security groups, you can actually associate 5 different security groups to a file system, specifically a mount target to a file system, to control access to that file system. In terms of controlling file and directory access, we are POSIX compliant. So you would use your standard Linux or Unix POSIX permissions to grant access or permission to individual files and directories. So to control access to manage file systems themselves through the API, you would use AWS Identity and Access Management. So we have action level and resource level permissions to control and grant access to which AWS user is able to manage these file systems. So that would be create file systems, manage the security groups associated with file systems, tag file systems, etc. So in terms of encryption, so we do offer encryption of data at rest and in transit. So a file system, when you create it, can be created with encryption of data at rest, as well as individual clients can enable encryption of data in transit, and that is done at the individual client level when you mount the file system. And in terms of compliance, so Amazon EFS is HIPAA eligible, and we offer BAA and PCI DSS compliance as well. So again, these are just some of the security models and compliance functionalities and features we have for EFS. So today it is available in 10 regions. And we plan on launching to all of our regions in the near future. So we are working very hard to get this out globally. So let's talk about economics. So as I mentioned earlier, so the economics of EFS is simple as well. So there are no minimum commitments or upfront fees associated with it. And since it's a fully managed service, there's no hardware to manage, so there's no need to provision storage in advance. And as I mentioned, it automatically grows and shrinks as you add and remove data. So again, there are no additional fees, no additional charges, just the standard billing dimensions. There's no request charges as well. So it's really a simple price per gigabyte per month for those in bursting throughput mode. And then when we talk about provision throughput mode, we'll talk about the billing dimensions of that file system as well. So with bursting throughput mode, there's a single pricing dimension. So you only pay for the amount of data you store in the file system. But what's included with the storage cost is it also includes 50 kilobytes per second throughput per gigabyte of data stored. And that equates to 50 megabytes per second per terabyte of data stored. So that's included in the price, in the storage price of the file system. And this is the only pricing dimension for file systems running in bursting throughput mode. When we talk about provision throughput mode, there is 2 pricing dimensions. So again, you have the standard storage price dimension as we had with bursting throughput mode, but we also add the throughput pricing dimension. And this is when you pay for the amount of provision throughput above what's included in the storage price. So anything above 50 kilobytes per second throughput per gigabyte of data stored that you provision, you will be charged for that at $6 per megabytes per second per month. So let's just go ahead and recall the sort of the DIY file storage costs we saw previously. So remember to keep in mind that these are, the costs vary. So if you're trying to do it yourself, you're going to have Amazon EC2 instance costs in both of these availability zones. You also have EBS volume costs. You have inter-AZ data transfer costs as well. So when you think about this, it all sort of adds up. So let's take a look at a simple TCO example. So say you're storing 500 gigabytes and say that you're using, typically EFS in relation to that cost is roughly 70% less than sort of a do-it-yourself. When you look at the storage that you need to provision, the compute and the data transfer cost associated with doing it yourself, you can see there's a substantial savings if you allow Amazon EFS to manage all of that hardware and all that infrastructure for you. So EFS is designed to serve the vast majority of file-based workloads. And it really covers a wide spectrum of performance needs. So the spectrum really runs from highly parallelized scale-out jobs, those that really require some of the highest possible throughput, things like big data applications or media workflows, all the way to single-threaded, latency-sensitive workloads, and really everything in between. So it is designed for a wide spectrum of needs. We have a large number of customers using Amazon EFS today, anywhere from JD Powers and Cisco. They're leveraging EFS for database backups. We also have customers using it for web serving and content management, like Thomson Reuters and FINRA. There's also big data and analytics workloads that are that some of our customers, like Monsanto, are using. So again, wide spectrum of use cases and customers using Amazon EFS today. So let's transition to phase 2, basically kicking the tires of EFS and seeing how EFS performs. So when you're testing out a new storage platform, what do you think about? So typically you want to think about the architecture around your use case, your workload. What do you need? What are some of those requirements? Next, you need to look at the functional testing. You want to, does my application functionally run on this new storage platform? Following that, you want to look at, okay, how does it perform? How can I get the best performance out of my application as well as the storage platform to best serve the needs of my application and my users? So let's dive a little deeper into the architecture of EFS, and we can show you what's happening. So when you create an Amazon EFS file system, you create this within a region. You do not create it within a VPC. So you create a file system within a region. You give access to that file system to resources within a VPC using a construct that we call mount targets. You would create a mount target, one mount target in each availability zone that the resources in your VPC are in. Then you have your NFS clients, or your resources would mount that file system using a single DNS name, and that will then allow you to gain access to that file system. These mount targets show up in your VPC as an ENI. So again, this is where you can control who has access to that file system data using your standard VPC security groups and VPC network ACLs. So when you take a look at all of these resources here in terms of the DNS name, the mount targets, and the file system itself, there are no single points of failure. There is high availability engineered and built into every aspect of a file system. So this is really where it differs from, say, a standard NAS or a standard file system that you would try to run yourself on Amazon EC2 and using Amazon EFS. So how do we start testing? So really, testing Amazon EFS is very, very simple. The first step is you create a file system. You can do this using a couple of clicks through the management console or a couple of API calls, and a file system is quickly created. Once that file system is created, you would create mount targets. And again, these show up as ENIs within your VPC, and that is the endpoint that your clients use to connect to that file system. And then on the client itself, you do your standard mount command to mount that file system, and now you have multiple clients accessing this NFS compliant file system within just really a matter of minutes. So when you're managing a file system, there's really not much to it. The APIs that we expose are, there's not a lot of them because it is a managed service. So we wanted to make this simple again. So there is an API to create a file system and manage the mount targets. Also to tag a file system, you can have up to 50 tags per file system. You can also, there's an API to manage the file system in terms of the throughput mode of your file system. And you can also view the details and delete a file system there. So not a lot of API calls because, again, we wanted to make this a very simple experience for you. So in terms of some of the best practices, so we do recommend when you're mounting an EFS file systems to mount it from a client running a Linux kernel 4 and above. So often I get asked from customers, well, what's the difference? If I have a client that's running maybe an older kernel version and a client that's running a current kernel version, what's the difference? What can I expect? So really what I want to do, I want to show you this. So let me go ahead and jump over to a demo. And let me show you what we can actually do in terms of, or what you could experience in terms of comparing an older kernel version with a new kernel version. So as you can see in my screenshot, I have an instance that's running kernel 3.14, and I have an instance running kernel 4.14. So we can do a simple uname-a, oops, if I could type. So we see that the top instance has is running 3.14. The bottom instance is running 4.14. Now, if we take a look at the mount command that I'm using, we see that both instances are running, are mounting the file system using NFS 4.1. So let's go ahead and run a simple test to see how fast we can generate, say, 1,024 files, small files, using these two instances in parallel and see what the difference is. So let me just go run over here and grab my script. I'm going to be using Small File. Small File is an open source tool that generates a lot of small files. And I'm going to go ahead and run this against both of these instances at the same time. So as we take a look at this, we'll see that the instance running kernel 4.14, we're able to generate 1,024 files in about 2 seconds. The instance running kernel 3.14 it took 8.5 seconds. So again, there are certain operations that the NFS protocol executes in parallel. They are actually serialized on older kernel versions. So again, open and close operations are one example where if they're executed in parallel by the application, they're not going to be executed parallel. They'll be actually executed serially within on the instance running older kernel versions. So again, this is just one example of some of the performance benefits of using a modern kernel version, really Linux kernel 4 and above. So let's go ahead and go back to the slides, and we'll finish up, show you another example of some of our best practices. So in terms of, oops, the other recommendation we have is the mount options themselves. So we do recommend mounting your file system using NFS 4.1. Even though we do support NFS 4.0, we do recommend 4.1. Again, there are some performance benefits mounting using the latest client protocol. We also released last year an EFS mount, or earlier this year, an EFS mount helper. The EFS mount helper is really a wrapper that is executed to mount the file system using NFS 4.1 and all of our recommended mount options. So it makes it very simple and easy to mount an EFS file system using the EFS file system ID. So we do recommend using the EFS mount helper. And again, that's just a wrapper to mount it using the NFS 4.1 protocol with our recommended mount options. As you can see here with the comparing the standard NFS mount command versus the EFS mount command, it's a much simpler operation to run in order to mount that file system. Just to give you an example of some of the benefits of using NFS Protocol 4.1 versus 4.0, let's go ahead and hop back to my demo, and I can show you what some of those differences are. So let's go ahead and run over to these two instances. So again, I have two new instances. One has a file system. We'll just let you know that both are running the latest kernel version of 4.14. When we take a look at the mount options, we see that this file system, the top one is mounted using NFS version 4.0. The bottom one is mounted using NFS version 4.1. So again, let's go ahead and compare and contrast these two. We'll go ahead and use that same command. So in this example, we're going to generate 1,024 files using small file in parallel, and we'll see the difference between the two. So we see that the NFS 4.1 already finished. We did that in just under 2 seconds, while it was a little over 8 seconds for the 4.0 or 4.0 client to connect. Again, some of the differences, open and close operations, even though they're executed in parallel by the application, in this example, small file, and because it was done by the same user ID or group ID, those operations are executed serially by the NFS 4.0 client versus running NFS 4.1, those are executed in parallel. So again, a big performance difference when you're running, for this type of operation, when you're running NFS 4.1 versus 4.0. So if we hop back to our presentation, we'll finish up. So again, for the functional testing, because EFS is POSIX compliant and we're fully compatible with NFS 4.1 and 4.0, your application, if it is already using and running on an NFS 4.0 file system or filer, it should just work. But again, we do recommend you test your application first to make sure and understand how it performs when accessing and using an EFS file system. So how do we test, or how should you test EFS performance? So what I want to do here is do really a quick demo, and I'll do a throughput test and an IOPS test to really compare the two. So let's go ahead and hop back to another instance. So I have a C5 2 extra large instance here. And let me go ahead and grab some scripts. So this first command, I'm going to be using DD, and I'm going to be generating a 2 gig file using a block size of 1 meg. And I'm going to see how fast I can do this. I'm writing to an EFS file system. So we see that I could generate 2 gigs of data in about 10 seconds. So averaging 213 megabytes a second. So as you noticed here, the sync operation that I'm using is F-sync. And basically what that means is I'm doing a data and metadata sync at the end of the 2 gig file. So maybe this really isn't really a part of reality, because typically you're going to be doing syncs in between as you're writing that data to this large file, and you may not wait until the end of the file before you make sure that that data and the metadata is synced. So this may not be a true test of how your application is accessing a file system, but I just wanted to show you up front what is possible with Amazon EFS depending on what your sync operations are. So if we change this up a little bit and we run that same command using a 1 meg block size, but we change the sync operation to now sync at the end of each 1 meg block, what do we see? So we do see a big difference. We're already at 11, 12 seconds, and we've only written around 300, 400 megabytes. So what has changed? We're still writing a 2 gig file. We're still using a 1 meg block size, but really the difference here is that we're doing a sync at the end of each 1 meg block. So after the end of each 1 meg block, we're issuing a sync command to the file system saying, go ahead and sync the data and metadata. And once that's done, we'll go ahead and we'll continue. So as you can see, the throughput really went from 213 megabytes a second when we did a sync at the end to around 27 megabytes a second when we're doing a sync at the end of each 1 meg block. So again, ask yourself, how is my application accessing that file system? How often does it do that sync operation? How often am I writing these smaller blocks to the file system? And what can I do to optimize the performance writing to EFS? Can I maybe consolidate or aggregate some of this I/O so I can have less frequent sync operations to ultimately improve throughput to the file system? So in this example, we completed the 2 gig write in 80 seconds. So again, a big difference from 10 seconds to 80 seconds, but it all depends on how is my application syncing or accessing the file system. Is it doing a lot of metadata operations really at the end of each 1 meg block, or is it doing it less frequently, maybe at the end of the entire write? So again, this is a good sort of compare and contrast between the two different types of operations. So what if, though, we were able to consolidate some of that data and say, you know what, let's change the block size. Instead of a 1 meg block size, we went to, say, a 16 meg block size. What would happen? So really what happens is, even though our mount options were using the maximum size of 1 meg for read and write, this operation of using a 16 meg block size and doing a sync at the end of 1 meg block, we just have less frequent metadata operations or these sync operations. So again, by just changing the size of the block in DD, we went from 80 seconds to 24 seconds because we're now able to write more data to that file system before we do a sync operation than we could before. So again, our throughput is improved and increases because of it. Well, let's go back to the 1 meg example, and now that we know that, you know, with a single thread we're able to get around 26 megabytes per second. Well, EFS is a parallel file system. It's massively parallelized across multiple storage nodes, across multiple availability zones within the region that you create the file system in. So what if we actually have multiple threads running in parallel? Could that improve performance? So in this example, I'm using new parallel and went back to my old DD operation using a 1 meg block size, doing a sync at the end of each 1 meg block. But because I have 4 running in parallel, each file is going to be creating a 512 megabyte file. In total, it'll still be 2 gigabytes. But because I have 4 running in parallel, I'm able to cut that time down now really in quarters. So now it takes 20 seconds to write 2 gigs of data using that same operation, that same sync operation, instead of 80 seconds when I had a single thread. So let's continue with this. So what happens if we actually combined the two? So let's say we increased the block size to 16 meg, as well as did multiple parallel operations using multiple threads. So now we're back down to 10 seconds. So again, we've sort of eliminated that barrier of doing a sync at the end of each 1 meg block by increasing the size of the block and running in parallel. Well, if your application is unable to maybe change the size of the block or aggregate your I/O, if you can spin up multiple threads and more threads, you're still able to benefit from this highly parallelized data structure and design that EFS has. So in this last example, I'll go ahead and run 16 threads, go back to a 1 meg block size, but now we're going to have 16 threads writing this data, these 2 gigs of data to EFS. And again, now we're down to 8 seconds. So extremely fast. This equates very close to around 250 megabytes a second writing to an EFS file system. So if you can parallelize your application and use multiple threads to read or write to EFS, you're able to improve the throughput and the performance of your application accessing an EFS file system. So let's go ahead and continue, and that was our throughput test. Let's do a quick IOPS test. So I've seen some customers run something very similar to this test. So what I'm doing here is I'm using a simple touch command to see how fast can I generate 1,024 0-byte files against EFS. So I went ahead and clicked on return, and so a couple of seconds have already passed, and I'm still waiting for this to return. So this is a very simple command. I'm trying to generate 1,024 0-byte files, and I'm still waiting. And I'm waiting. And I'm waiting, and I waited 18 seconds. So to me, yes, this seemed like a long time. 18 seconds to generate really zero data. All I'm doing is metadata operations generating 1,024 files. So if I compare this to, say, EBS, so attached to this instance, I have an EBS volume. If I run this against an EBS volume attached to this instance, I can actually do this in around 3 seconds. So again, a big difference. But as I showed in the previous throughput example, what if, because I know a little bit more about an EFS file system now, and that by highly parallelizing data access to this file system, I'm able to improve throughput. Can I also improve IOPS? Let's go ahead and see if we can. So in this example, I'm going to use 32 threads to generate 1,024 files. I'm using new parallel to do that. So I went ahead and kicked this off, and we'll see that, we're not going to wait 18 seconds to complete this. Actually, let me click. We actually cut that down, and now we're just under 10 seconds. So while we've improved the performance of this test, we're still not down to the level where we would like to be. Well, I also know a little bit more about an EFS file system and just file systems in general, sort of in the Linux or Unix world. So we have this concept, this construct called an inode. So inodes are very common among Linux file systems, and an inode is really metadata that's associated with file system objects, either files themselves or directories. And when you're doing a lot of metadata operations against an inode, you could experience what we call inode contention. So that is really when you're trying to update a lot of metadata operations against an inode, and this contention could impact performance. So what if we changed up my operation a little bit and actually said, I have 32 threads writing. Why don't I actually have each thread writing to its own subdirectory? How could that improve performance? So in this example, we're going to go ahead and have 32 threads writing 32 files in their own directories. And now I'm able to cut that down to a second. So again, we went from 18 seconds down to a second by just parallelizing access and avoiding inode contention by writing into multiple subdirectories and touching multiple inodes. So again, these are some of the tips and tricks that you can use to improve not only the throughput, as we saw earlier, but also the IOPS when you're accessing an EFS file system. So if you go back to our presentation, we can briefly look at the results of some of the throughput tests that we ran. So this summarizes an earlier test I did, where with a single thread with a 1 meg block size, it took us a long time to, to generate that data. But as we add more threads, and as we increase the block size of the file system, we're able to maximize the throughput from that instance to EFS. And in this example, we were able to get up to 250 megabytes a second by just changing those two attributes of our data access. As well as with our IOPS test, really going from a single-threaded operation to a multi-threaded operation, accessing multiple subdirectories, avoiding inode contention, we're able to dramatically improve the IOPS and performance to EFS. So Now let's take a look at the next phase, and that's ingest. How do I quickly ingest data into EFS? So typically we think about where's the data coming from and how we can easily move the data as fast as possible. So typically we see data coming in to EFS from either an on-prem data center, maybe from an EBS volume or other cloud offerings, other software appliances within the cloud, and also coming from Amazon S3. So when you're coming from on-prem or even from, say, EC2, we do have a tool called EFS File Sync. And EFS File Sync is a management console tool that allows you to ingest data into EFS very quickly. So it is very simple to get up and running. It is, as I mentioned, a management console. So you go into the management console, you set up an agent and a task, and then through the console, you execute that task and it'll ingest data into your file system. It is very fast. So we leverage some of the functionality that I showed you earlier by using multiple threads. And we see that you can get up to 5 times better performance using EFS File Sync than you would if you use the standard Linux copy commands. And it is secure, so the connection is encrypted, so your data is secured. You don't need to have a direct connect. You don't need to have a VPN connection. The data is secured from your data center to the EFS file system using Amazon EFS File Sync. So again, very easy way to ingest data into EFS. Now, if you don't have the ability to do that, or if for some reason you elect not to use EFS File Sync, there are other tools you can use to ingest data and move data into an EFS file system. So these are just some of the ones that I wanted to quickly demonstrate. So as an example, rsync. I think a lot of customers, if I asked you right now, what tool would you use to move copy into a file system? A lot of you would usually, pull out rsync out of your toolbox and said, yeah, I'm going to go ahead and use rsync. So I'm going to go ahead and show you a demonstration of what that would look like if you were using rsync to ingest data into EFS. So let me just go ahead and clear my screen, and I'm going to give you a quick look at what we have. So I'm going to go back to that same instance we were using before. And let's go ahead and I'm going to show you what we have. So on my EBS volume, I have 5 gigs of data. I have 5,000 files. So roughly each file is 1 meg in size. And they're going to vary from a couple of kilobytes to a couple of megabytes, but on average, they're 1 meg in size. So what I want to do is I want to copy that data from my EBS volume to my EFS file system as quickly as I can. So in this first example, we're going to go ahead and use rsync. So I'm going to use nload to take a look at what that throughput is. So if we look here, we're seeing that, yeah, maybe on average we're getting, right now it's 7 or 8, but we were a little higher. So I would say maybe average we're getting 10, 11 megabytes per second throughput to EFS file system from this EBS volumes using rsync. So why is rsync so slow? Any ideas? So a couple of things we know about rsync. One, it's single-threaded. And 2, it's very chatty. So again, if we go back to some of my previous examples with our throughput and IOPS demo, that if it's single-threaded and there's a lot of network operations going on, then you don't get the best throughput. You don't get the best performance to EFS. So one thing we want to do is we want to say, you know what, let's not use rsync. We want to use something else. So another example is CP. So let's see how CP performs against EFS. So this is a standard CP command, copying data from EBS to EFS. So let's go ahead and take a look at nload again. And we'll see that, we get a little better performance, not much, but we get a little better performance than rsync. Well, why? Well, CP is what? Single-threaded as well. So again, we're not taking advantage of this parallel data storage design that EFS has. It is single-threaded, but it's not as chatty as rsync. And I know there's options you can sort of disable on rsync to make it less chatty. But overall, it's still going to be rsync is going to be more chatty than CP. So let's go ahead and kill this. So just make sure that everything is clean, and it is. So let's keep going and do some other tests. So in this example, I'm just going to create a variable. Now I'm going to show some multi-threaded examples. And now I just created a variable that said, okay, for each virtual CPU I have on this instance, I want to use 4 threads. So I'm going to use this. So next example is FP Sync. If you're familiar with FPART or FP Sync, this is a multi-threaded rsync. So if we take a look at how this is performing, instead of getting 10, 11 megabytes a second, now we're getting in the mid-20s, high 20s. So definitely we see an improvement. But again, because rsync is very chatty and we are running multiple threads, not the most efficient tool. So let's go ahead and kill this. Once we start going multiple threads, it's a little harder to kill. Let's just make sure that everything is clear, and it is. Okay, so that's FP Sync. Now let's use new parallel and CP. So in this example, we're just using new parallel, standard CP. We're managing the threads themselves. So we're getting much better throughput than even FP Sync. So now we're getting maybe 60, 70 megabytes per second throughput. So very good throughput. This is where it even makes it even harder. So we got to kill that. Let's make sure everything looks good. All right. So this last example, we're going to use sort of a combination of a number of things. So let's go ahead and do this. So here I'm using new parallel and FPART. So what I just did there with FPART, I generated a partition file. And partition file looks something like this. It's a simple file that has an index or a directory of all the objects in the source that I want to copy. And I'm going to pass this to my next tool. So the next tool is CPIO. So some of you may be familiar with CPIO. CPIO is a tool that a lot of you may use for archiving purposes. But there are 3 different modes for CPIO. There's copy in, copy out, and what we're going to use copy pass. And with copy pass, it actually is able to take a partition file as the input. So it'll look at this partition file using new parallel. It'll carve that partition file up, give it to multiple threads, and each thread will now copy a part of that data from source to destination. So let's go ahead and kick this off. We'll do a quick end load. And now we're getting much better throughput. We're getting 120, 130 megabytes a second. So we're getting much faster throughput to Amazon EFS using a multi-threaded tool that is very network friendly, if I can say that. Something that is not chatty. And we see here within a few seconds, we're able to transfer 5 gigs of data. And these are not large files. So these are, some of them, kilobytes in size, up to maybe a couple of megabytes in size. We're able to transfer all 5,000 of these files in only 39 seconds. So again, we want to use the best tool for the job, and by parallelizing your ingest commands to EFS, you're able to achieve higher levels of throughput. So let's go back to the presentation and we'll finish off. So as I just showed you, when we compare the different file operation commands, copy commands that I use, we definitely go from poor with rsync, because it is very chatty, single-threaded, all the way to FPART, CPIO, and new parallel. So as an example, I ran this a little earlier on a C5 large instance, and it really went anywhere from getting 11, 12 megabytes a second all the way up to 122 megabytes a second. So again, same source, same destination, just changing the tool makes a big difference. And we're taking advantage of this distributed data storage design of EFS. So let's go ahead and talk about run. So when you're running a file system, what do you need to do? Well, really not much. You can view some of the metrics in CloudWatch, and you can get the API calls within CloudTrail, and you can perform backups. But because it is a managed service, there's really not much to do. So all the API calls that are executed against your file system to manage it, creating file systems, managing the mount targets, all of that is recorded and presented to you via CloudTrail, and that's available to you in that S3 bucket associated with your CloudTrail. In terms of CloudWatch, we have 8 metrics available to you to monitor and see how your application is driving that EFS file system. And I've actually created a dashboard to help you understand how your application is driving that file system. So if you take a look at the URL here, I created a GitHub repository with an EFS tutorial that will actually step through some of these operations I did today, and it also has a link to a CloudFormation template that will create this dashboard for you. The backup solution is also very simple. So we do have an EFS to EFS backup solution. It is a CloudFormation template that will spin up an environment that will help you back up your EFS file system to another EFS file system within the same region, and you can set it on a schedule. So again, a very simple, easy process to use. So in terms of wrapping up, let's go ahead and walk through the best practices. So again, general purpose performance mode file systems, we recommend starting out with that. We also recommend starting out with bursting throughput mode, because again, you can change that to provision throughput mode, but we recommend starting out with bursting throughput mode to see how your application performs. Use Linux kernel 4 and above, mount using NFS 4.0 using our EFS mount helper. Aggregate your I/O with larger I/O size, use multiple threads, scale this out across multiple instances as well, and try to write or access the file system using multiple directories. Don't put all your eggs in one basket. Don't put 10 million files in one directory, then try to access all this data in parallel. It's better to spread these across multiple subdirectories. And monitor your file system. Use the dashboard that I showed you. Use CloudWatch to see how your application is driving that file system. There's a lot of information online to help you understand more about EFS. And again, this is a link to the tutorial where you can go and actually step through some of the operations I showed you today and get access to that CloudFormation template and that dashboard. So with that said, I want to thank everyone, and I turn it back over to the moderators.